A very good morning to everyone. This is Manoj Kumar Rampelli. Now I am going to discuss in brief about my paper, Advantage of Extended Kalman Filter over Discrete Kalman Filter. Okay, now coming to the application of this Kalman filter is that it is state estimation. Okay, what is state estimation? In general, state estimation is used to reduce the measurement errors so that we can get an accurate data which can be used for controlling our power system generation. We all know that controlling is a important aspect in any application. So by considering this, we can say that state estimation is the backbone for the entire energy management systems, because using that data as input only we are going to control and monitor this entire power system networks. So that is our application, and we are using for that application state estimation techniques known as Kalman filtering techniques. Why only Kalman filters? Okay, so there are many methods for estimating states. The basic method is that weighted least squares method. Why can't we apply that method here? And that basic weighted least square method is only for static state estimation. That means that method considers that entire power system network is static in nature. But in practical, if we consider that power system network is not at all static and it is dynamic in nature. So we need to consider the dynamic nature of the system. For that we need to go for Kalman filters. And this Kalman filtering is a two-step process. First, we are going to predict the future states, and after predicting those states, we are going to correct them by using Kalman gain. Okay, and those entire algorithms are already existed in this literature. But what my work in this paper? I have applied all those algorithms for a power system network which I have considered it as IEEE 14 bus network, and my state estimates are voltage and its angle at all 14 buses. Okay, so my states are voltage and its angle, and my measurements are active power flows, active injections, as well as reactive power flows and reactive power injections. So there are mainly three types of Kalman filtering techniques: discrete, uncentered and extended. Discrete is for linear functions, that is measurement function and process function has to be linear. Coming to the extended and uncentered, we can go for nonlinear functions. So let us consider our measurement function active power flows. It is a linear function after approximations, but in general it is non-linear function of state variables. So for applying discrete Kalman filter, we need to approximate it so that it will become into linear form. After assuming some assumptions like voltage at all buses is equal to 1 pu, we are going to approximate that into linear one. So if we consider the voltage at all buses is 1 pu, the state variable is only one, that is angle at all buses. Okay, we can't consider two state variables to be estimated if we use discrete Kalman filter, right? Because if we use two state variables form, the function becomes non-linear. That is the limitation of discrete Kalman filter. Then what about extended? Extended can be used to estimate the functions of non-linear also. So in an extended case, we can go for both variables estimation using extended Kalman filter. Okay, so finally it has been decided that for estimating only angle we need to go for discrete Kalman filter, whereas to estimate the both angle and its voltage we need to go for extended Kalman filter, right? So finally our state estimation variables have been decided, and the algorithm which has to be used for estimating those state variables has also been decided. Now the estimation has been done using the existed algorithms. So finally, how we are going to analyze its performance? For analyzing its performance, we need to compare those estimation techniques with measurements data, right? Our measurement data is active power flows and reactive power flows also. Okay, so let us take for comparison only active power flows. We have state estimates, voltage and its angle, but the measurements are of the active power flows. But how to compare these two? So for that purpose, I have converted those state variables into active power flows. How? It is very simple, right? Because active power flows is a function of voltage and its angle, right? Previously, for measurement data, we are taking true values, like we are considering some standard data of IEEE 14 bus as true values. And for those data, we are adding some noise of some standard deviation. Okay, after adding noise, it is becoming measurement data. The standard data is true and we are adding to that noise, and then that is becoming measurement data, which is of active power flows. And using these state estimates, we are finding active power flows, which is becoming the values of active power flows using estimates, not using measurements. Okay, we are estimating and then we are finding active power flows. So like this, we can compare state estimation techniques by using measurement data, and the plots or results for these two techniques have been shown in my paper. And I also calculated the squared error using both methods, that is discrete and also extended, and from those results we can find that extended Kalman filter is superior in performance compared with the discrete Kalman filter. And like this, I have compared these two techniques for estimating states of IEEE 14 bus network. Thank you very much. In addition to my discussion here in this video, I am also attaching my important slides regarding this paper. Please go through them. Okay.